Alright, welcome back to the classroom. My name is Mr. Wong. We're going through part 2 of a lesson where we discuss about nuclear fusion and nuclear half-life. So we've already talked about nuclear half-life, that was in the previous video. What we're going to be talking about in the second part is the concept of nuclear fusion. And more specifically, we're going to look at how nuclear fusion causes the conservation of mass energy through spontaneous and artificial nuclear transmutations. And we're going to look at what accounts for this release of energy when the process of nuclear fusion occurs. Let's firstly look at a common example of where we see nuclear fusion, and that's inside the sun. Now, inside the sun, a common thing that will happen is you'll have two low mass nuclei, so filled with protons and neutrons, will combine together to form a heavier nucleotide, which in this case would release energy because of, and you can see the energy is being released here, the reason being is because mass defect. Now think about it this way, to hold the nucleus together, that energy to hold it together, we call it the binding energy. Okay? What we see in a nuclear fusion reaction, obviously this image here is a nuclear fission, but what we see in a nuclear fusion is there's always going to be some kind of mass defect where the mass of the reactants and the mass of the products don't equal, and that difference in mass is attributed to that mass being converted into energy. That mass difference is known as the mass defect. According to Einstein's famous equation E equals mc squared, that mass you see here can be the mass defect, the mass lost by a particle when it's gone through some kind of nuclear reaction, when placed in proportion with the speed of light. That's the amount of energy that will be released when the particle experiences mass defect. So you can see how when energy goes down, the mass of that particular atom goes up. So that's kind of what we're talking about with mass energy equivalence. Another way we can actually measure mass defect is by the unit, atomic mass units. Sometimes you'll find that the units can be given as simply just lowercase u. Otherwise, if we're measuring like so, we are measuring in mega electron volts. Remember, if you want to convert this back into joules, you simply times this whatever value, n value you have for that energy, into the charge of the electron. So this bit here is the charge of the electron, and here is to account for the mega, and that will convert our values back into joules. So that's what's happening when something's going through nuclear fusion reaction. That mass defect will cause the production of this energy. So let's quickly talk about some multiple choices. If you don't want to be spoiled, now's the time to pause the video. Okay, let's go through the answers. So what name do we give the energy equivalent of the mass defect? We call that the binding energy. So whatever mass was lost, it was because of the energy that was holding the nucleus together. Question B, what is meant by the equivalence of mass and energy? What that basically tells you is that mass has an energy equivalent and energy has a mass equivalent. So they are interchangeable. They can be, under very specific conditions, interchanged with each other. If we're trying to do a quick recap of mass defect, just remember in all nuclear reactions the loss in mass is attributed to by comparison to the individual protons and neutrons of that atom or of that nucleus. The binding energy is the minimum energy required to separate the nucleus from its component parts. So that's the amount of energy you'll need to separate your electrons, your protons, your neutrons away from each other. This energy is released regardless of what type of nuclear reaction you have. It can be for fusion, it can be for fission. This energy difference can be resolved by Einstein's equation E equals mc squared. Remember, we're dealing with really fast moving waves here in terms of gamma rays, and so that's why we see really large amounts of energy occurring, and that's the interchangeability between the mass and the energy for this equation. You also need to understand the greater the binding energy, so the greater amount of energy you're putting into the bonds, the harder it is to pull the nucleus apart. So the greater the binding energy, the more difficult it is to pull the protons and electrons away from each other. If we have a look at a nice little chart, it paints a really nice illustration of the energies each nucleus of the isotope produces. What we see here, we can see with hydrogen 1, hydrogen 2, and then obviously you have hydrogen 3 here, or lithium. Now what's happening here is you can see for every new nucleotide, so from one small, or we can say we have two small nuclei, and we make one large nuclei, okay, the overall energy that's being released gets higher until about you reach the isotope of iron, after which the overall energy per a nucleon, so per the protons and neutrons, that actually begins to drop down in the nucleus of more heavy elements. Now the reason for that is the greater release. So the reason being is the how to put it, the nucleus is beginning to get less and less stable. And what we know is it actually costs more energy to cause the fusion of these atoms than it is the actual breaking part. So from this point onwards, the energy input is much higher than our energy output through the formation of these nucleus or nuclei. Okay, what won't change though is the overall energy of the nucleon. So the overall energy to sort of hold everything together, or what we call binding energy, that value is still going up in comparison to what we see here with the energy that's per individual particle inside that nucleus. So, doing a quick comparison, fusion or fission. In this lesson we are talking about nuclear fusion, which is where two smaller atomic nuclei come together and in that case release energy. You might be more familiar with this concept of nuclear fission, where a radioactive source is agitated by a really slow moving neutron, and it begins to break itself apart. Usually it breaks itself apart into 3 neutrons and spreads in all directions. When it comes to nuclear fusion, it's the process at which having two young nuclei or two nuclei come together to form a larger nucleus. Fusion requires an enormous amount of energy input, such as extreme pressure and heat. That's why nuclear fusion only really ever occurs inside the core of the sun, so inside the core of the sun. We also talked about the fact that nuclear fusion reactions tend to release a much higher quantity of energy than fission reaction does. And to my understanding, this is due to a greater proportion of the mass energy available compared to the fission results. So that's what we had there. If you look at a direct comparison, the binding energy per nucleon, if you're starting from hydrogen, increases continuously until you get to iron 56. The energy that releases comes from the mass defect of the ongoing nuclear reaction. So for the fusion of heavier nuclei, so anything over here, to actually cause these atoms to want to bond together, you need this sort of a special and so for the heavier nuclei, a net input of energy will be required in order to get these heavier molecules or heavier nuclei to try and collide to each other. If we have a look at the function of nuclear heavy-I, it's quite important, particularly with our discovery of the elements of the periodic table. So you can see here, I've shown you this before, different elements of the periodic table are formed by different types of interaction in space. The first two lightest elements is caused by the Big Bang fusion. So there you go. Without this process in nature, we wouldn't have the periodic table. You and I won't be alive either. Some of the procedures in which stars generate heat through nuclear reactions is 1, the proton-proton chain, and 2, the carbon-nitrogen-oxygen chain. Now if you recall, the proton-proton chain, you have 4 protons in total, one bonding after the other, to form a whole helium nuclei. The CNO process is slightly different, so instead of using chemicals or using the radius to collide with our desired atom, we use these heavy elements as guides in which to help facilitate the release of photons and then forming the ideal helium nuclei that we were hoping for to power and generate the sun. Okay, so put generally, the overall timeline of a proton-proton chain reaction is given here. We have 4 hydrogen atoms that will create and form together to create a helium-4 nuclei, 2 positrons, 2 neutrinos, and 2 gamma rays. If we flipped it around and examined the net equation for a carbon-nitrogen-oxygen cycle, again you have something very similar to the very first one. You have the 4 protons that combine together to generate helium, and then besides that you have your 2 positrons, 2 neutrinos, and then 3 gamma rays. So that's the idea here, that the CNO is a catalyst to facilitate the cycle, but it's not part of the actual response. Alright, so let's account for the energy released in nuclear fusion reactions. We already talked about this being due to mass defect. Let's perform some calculations to actually look at the overall effect that mass defect has on energy being released in fusion. So we have an equation where we have hydrogen 2 plus hydrogen 3. they'll combine together to make helium-4 and 1 neutron. So what could the mass or the mass defect be? Okay, so we need to find mass defect, and then what we're trying to find is the energy. So mass defect, we have the units of the reactant side, so let's write that first. That'll be subtracted by the mass of the products on the right hand side. And that's our mass defect there. So the number I get if I plug it into my, okay, so we get a mass defect of 0.0188 atomic mass unit. The energy that will be generated from this is the atomic mass unit defect times 931.5. So let's do that again. And the energy we get here is 17.5122 mega electron volts. If you want to convert this into joules, you need to make sure to times this by the charge of the electron times 10 to the power 6 because of that mega electron volts. Okay, so that's how you do that question there. And that's given to your units there. The next one we have is the fusion of carbon-12 with an alpha particle. The equation is already written out for you here. If you know the following masses, find the energy released each time a carbon-12 and helium-4 nucleus fuse to produce an oxygen-16 nucleus. So pause it now if you want to have a go. If not, let me show you how to do it. Okay, so firstly we need to work out the total mass defect. Now we want to work out the mass of this side and then subtract it by the mass of this side here. That'll be the mass defect we're looking for. And so I find that to be 0.0054 atomic mass units. In the next equation we're going to look at, the energy release is the mass defect times our number here again, and that equals to 5.0301 mega electron volts. Convert that into joules, that's the value we get here. So that's a demonstration of how mass defect in a nuclear fusion reaction will release the energy that we're witnessing in these calculations here. Alright, the last one we have is a proton fused with deuterium, which is hydrogen 2 to form helium-3. Using the following data that we have here, find the mass defect, find the energy released. Again, pause this video here if you want to have a go yourself. If not, let me now explain. So the mass defect that we get, again, the reactants minus our products, or vice versa, in this case just needs to be the change, is that value given to you here. And then what we have is the energy released for this reaction. Substitute it back to our formula. That's the total amount of energy we have, about 30.565 mega electron volts. To convert that into joules, we get this value here. Okay, and so that kind of concludes and demonstrates how the mass defect in a nuclear reaction will cause the release of energy. Now you need to understand one thing: the likelihood of nuclear fusion occurring is very rare. As a matter of fact, majority of the ways we use nuclear energy or nuclear reactions to produce energy are all nuclear fission, which is exactly what we're going to be talking about in the next lesson. As a matter of fact, the only time we really see nuclear fusion occur is under really extreme temperatures and pressure, which is the center of the star. Anyhow, if you found this video useful, please obviously watch the other series, give it a like if you would be generous. Until next time, which is when we talk about nuclear fission, thank you for watching and coming into the classroom.